Somewhere past the edge of our solar system, a beam of light is racing away at 670 million miles per hour. Nothing we have ever built can catch it. Every rocket, every probe, every crew we send slams into the same invisible wall. But a team of physicists just published math that breaks through it. A warp bubble that bends space. A wormhole held open with strange energy. A ship that arrives before it leaves. If this mission briefing intrigues you, hit subscribe and stay with us. Strap in, we are launching now. Every mission planner on Earth shares the same nightmare. You draw up the trajectory, you calculate the fuel, you pick the destination, and then you run into a ceiling that refuses to move. That ceiling is 670 million miles per hour, the speed of light. Nothing we have ever launched has come close to touching it. The fastest object humans ever built, the Parker Solar Probe, screams through space at roughly 430,000 miles per hour. Impressive until you compare it to the cosmic limit. Parker moves at less than 0.1% of the speed of light, a snail racing a bullet train. The problem is written into the bones of the universe. Einstein figured it out in 1905, sitting at a patent clerk's desk in Switzerland. He noticed something strange about light. No matter how fast you chase a beam, it always moves away from you at the same speed. You can run toward it, you can run away from it. The number never changes, 670 million miles per hour every time. That discovery broke classical physics in half. If light refuses to slow down or speed up relative to you, then something else has to bend. And what bends, Einstein realized, is time itself, space itself, mass itself. The faster you go, the heavier you get. The faster you go, the slower your clock ticks compared to someone standing still. Here is the part that wrecks every deep space mission on the drawing board. The closer you push toward light speed, the more energy it takes to accelerate even 1 extra mile per hour. At 90% of light speed, your ship already weighs more than twice what it weighed at launch. At 99%, roughly 7 times heavier. Push further, and the curve shoots toward infinity. To actually reach the speed of light, you would need infinite fuel to push infinite mass. The universe slams the door in your face. This is why the nearest star beyond our own, Proxima Centauri, sits so cruelly out of reach. It is only about 4.25 light years away. A photon crosses that gap in a little over 4 years. Our best chemical rockets would take around 40,000 years. A human civilization would rise, fall, be forgotten, and rise again before the ship arrived. For most of the 20th century, physicists treated this wall as permanent, a law of nature, an ending to the story before it could start. Every Starship blueprint in every engineering journal ran into the same cold math, and every author shrugged and admitted defeat. Then, slowly, quietly, that consensus began to crack. A Mexican physicist working in Wales sketched out an equation on a napkin in 1994. A laboratory at Houston started running tiny experiments most universities refused to touch. A paper published in 2021 claimed the warp drive could work without the impossible ingredient everyone thought it needed. The speed of light is still the rule, but the rule, some teams now believe, has a loophole, a way around, not through. Before we chase that loophole into the lab, we need to understand exactly why the wall stands so stubbornly. Why a simple flashlight held in the right hands rewrites the laws of motion. Picture a train racing across open country at 500 miles per hour. Inside the last car, you're standing with a flashlight, pointing it straight ahead. You flick it on. Common sense says the beam leaves your flashlight at light speed plus the train's speed. 670 million miles per hour, plus 500. A tiny bonus, but a bonus. Common sense is wrong. Someone standing in a field watching the train go by measures that exact same beam. They clock it at 670 million miles per hour, not a single mile faster. The train's motion adds nothing. The beam moves at the same speed for you inside the train, for the observer in the field, for a pilot flying overhead. Every single witness, no matter how fast they themselves are moving, measures the same number. Physicists ran this experiment for real in 1887. 2 American researchers, Albert Michelson and Edward Morley, built a machine in a Cleveland basement designed to catch light in the act of changing speed. Earth itself is a moving train. It hurtles around our star at 67,000 miles per hour. They expected beams shot along Earth's direction of travel to move faster than beams shot sideways. They set up mirrors, split a light source in two, and compared the arrival times with extraordinary precision. The numbers came back identical. Every direction, every time. The experiment was repeated, refined, repeated again. The answer never changed. Light did not care about Earth's motion. Light did not care about anyone's motion. Michelson was devastated. He spent the rest of his life believing he had failed. He was wrong about that too. He had just proven the single strangest fact in physics. Something had to give to make this work. If the speed stays constant, then the readings would drift by miles within a day. The flashlight on the train shows you why no rocket can outrun a photon. Every attempt to add your ship's speed to the speed of light gets cancelled out by space and time bending to protect that constant. You pour in more fuel, space shrinks ahead of you, time slows around you, the beam still pulls away at the same pace it always did. A chemical rocket cannot win this fight. A nuclear rocket cannot win it. Even an antimatter rocket, burning the most energetic fuel physics allows, bumps against the same barrier. Every engine we know how to build is playing the same losing game against the same unblinking number. Which forces a different question entirely. What if you stop trying to move the ship faster and start moving something else? Every rocket scientist eventually meets the same enemy, and it is not gravity, it is the fuel. The rule is simple and brutal. To go faster, you burn fuel. But fuel itself has weight, and the fuel you need to push that extra fuel also has weight, and the fuel you need to push the fuel that pushes the fuel, that has weight too. The stack grows and grows and grows until the rocket you designed for a modest trip looks like a skyscraper of exploding liquid. Engineers call this the tyranny of the rocket equation. A Russian schoolteacher named Konstantin Tsiolkovsky wrote it down in 1897, scribbling in a notebook in a small town southwest of Moscow. He was deaf, self-taught, mostly ignored. His math now governs every space program on Earth. His equation says this: the mass of a rocket at launch grows exponentially with the speed you want to reach. Want to double your top speed with the same engine? You do not need twice the fuel. You need the original fuel, multiplied by itself several times over. A small jump in speed demands a monstrous jump in mass. A Saturn V rocket, the tower that launched astronauts toward the moon, weighed about 6.5 million pounds at liftoff. The crew capsule that actually reached the moon weighed about 100,000 pounds. Less than 2% of the launch mass became payload. The other 98% was fuel, tanks, and throwaway hardware burned off on the way up. Almost the entire rocket exists to lift a sliver of itself. Now scale that up to interstellar speeds. Imagine trying to push a spacecraft to 10% of light speed using ordinary rocket fuel. The math does not just get worse, it breaks. A team at NASA ran the numbers in the 1980s for a crewed mission to Alpha Centauri using chemical engines. The required fuel mass came out greater than the mass of every planet in our solar system combined. More rocket fuel than there is rock and metal in Jupiter. The trap gets worse. Even if you somehow found that much fuel, you would have to carry it. Every extra pound of propellant demands even more propellant to move it. The curve steepens into a wall the same way the light speed barrier does. The numbers start chasing their own tail. Engineers have tried to escape the trap by finding stronger fuels. Liquid hydrogen packs more punch per pound than kerosene. Nuclear thermal rockets tested on the ground in the 1960s would double the efficiency again. Ion drives, sipping xenon gas in a whisper of thrust, push even further. The Dawn probe that orbited the asteroid Vesta ran on ion engines. It reached roughly 25,000 miles per hour above its launch speed after years of firing. Even with those advances, the best any realistic rocket could achieve is a few percent of light speed. A journey to the nearest star would still take centuries. The crew would have to be unborn when the ship left, and strangers to Earth when they arrived. The rocket equation is the reason deep space looks so empty on mission timelines. It is also the reason physicists started wondering if the answer lives somewhere else entirely. Not in a better engine, but in a trick no rocket has ever tried. Proxima Centauri is our closest neighbour beyond our own star system. On a clear night in the southern hemisphere, you can spot the Alpha Centauri system with your bare eyes. That bright point of light hangs just over 4 light-years away. 4 light-years sounds friendly. It is not. A light-year is the distance light travels in 1 year. 6 trillion miles. Stretch that out by more than 4, and you get a gap roughly 25 trillion miles wide. 25,000 billion miles. If you started counting each mile out loud, 1 per second, you would still be counting when the universe itself died of heat death. The Voyager 1 probe, launched in 1977, is the farthest human-made object from Earth. It is currently drifting through interstellar space at around 38,000 miles per hour. Fast by car standards, pathetic by star standards. Voyager would need roughly 75,000 years to reach Proxima Centauri, if it were even pointed that way. It is not. A modern, purpose-built starship using chemical rockets could trim that down to about 40,000 years. That is longer than the entire span of recorded human civilization. Longer than the time since cave paintings appeared on walls in southern France. Launch the ship today, and the crew's descendants would not arrive until a point in the future so distant it has no name. 40,000 years of what exactly? Life support, radiation shielding, food, water, air, replacement parts for every system on board, a civilization sealed inside a hull generations deep. The original crew would die, their children would die, their children's children would die. Somewhere around generation 1500, their descendants would finally see a new star growing in the viewport. Those descendants would speak a language nobody on Earth could understand. They would remember Earth as a myth. The reason their ancestors climbed into the ship would be lost. Mission planners do not like this. It is not a mission. It is an exile. Ion drives could cut the trip to perhaps 10,000 years. Nuclear thermal rockets, roughly similar. Even the most optimistic fusion drives on paper, burning hydrogen the way stars do, would need a century or two at minimum. A century of sealed life support, with zero resupply, zero rescue, zero communication fast enough to matter. Radio signals travel at light speed. Send a message home from Proxima, and your family waits more than 4 years for it to arrive. Another 4 years for their reply. Every conversation becomes a decade-long exchange. Every emergency becomes a funeral by the time Earth can respond. This is the cold floor mission planners keep hitting. The speed of light is not just a physics problem. It is a calendar problem. It turns every star into a tomb. It turns every crew into pioneers who will never come home. Which is why a small group of physicists in the early 1990s stopped asking how to build a faster rocket. They asked something else. What if the ship never moves at all? What if space moves, and the ship just rides along? One paper, one equation, one quiet Thursday in a physics journal changed the conversation forever. In 1994, a Mexican physicist named Miguel Alcubierre was sitting at his desk in Cardiff, Wales. He had just finished watching an old science fiction show, the one with the starship that jumped between stars at impossible speeds. He found himself wondering a simple question. If you ignore the engine entirely, what shape would space itself have to take to let a ship cross the galaxy in a week? Most physicists would have smiled and moved on. Alcubierre pulled out a sheet of paper and started writing equations. He worked with Einstein's field equations, the same math that describes how mass bends space and time. The equations are famously ugly. They have 10 interlocking pieces that twist around each other like tangled vines. Solving them for any real situation is brutal. Physicists usually start with a desired physical situation and try to find the math that matches. Alcubierre did the opposite. He started with the outcome he wanted, faster than light travel, and asked the equations what kind of space would produce it. The answer came back surprisingly clean. Imagine a flat sheet of rubber stretched between two posts. That sheet is space. Put a marble on it. The marble is your spacecraft. Now pinch the rubber in front of the marble. It scrunches up, contracts, pulls itself toward the marble. Behind the marble, stretch the rubber outward. It expands, pushes the marble forward from behind. The marble has not moved along the sheet. The sheet has moved around the marble. Space in front contracts. Space behind expands. The marble rides the wave, and the wave has no speed limit because Einstein's rules only restrict objects moving through space. They say nothing about space itself moving. Alcubierre had found a loophole written into the universe's own rulebook. He called it a warp bubble. Inside the bubble, the spacecraft sits perfectly still. No acceleration, no crushing forces. A cup of coffee on the control panel would never spill. Outside the bubble, space itself races forward faster than light. The ship surfs along without ever technically breaking the speed limit. When he published the paper in the journal Classical and Quantum Gravity, the physics world paused. The math worked. Nobody could find an error. A Cambridge-trained physicist had just shown that faster-than-light travel was allowed by the same equations that govern black holes and the Big Bang. Then came the catch. Alcubierre's bubble required a specific ingredient to maintain its shape, something called negative energy density, a type of energy with less energy than empty space. Most physicists at the time considered it pure fantasy. Some quantum effects hinted it might exist in trace amounts, but nobody had ever seen it in bulk. Early estimates suggested a working warp bubble would need negative energy equal to the mass of the entire planet Jupiter, converted into antimatter-grade fuel, confined into a ring around the ship. The warp drive, in other words, was mathematically possible and practically absurd. A Ferrari engine that only runs on unicorn milk. For a decade, the idea sat on a shelf, a beautiful curiosity, a thought experiment nobody could build. Then the numbers started getting smaller, and a lab in Texas started running experiments that nobody had expected to see in their lifetime. To understand why the Alcubierre drive gets around the speed of light, you have to stop thinking about rockets and start thinking about rivers. Picture a boat floating on a river. The boat has a small motor. The motor can only push the boat through the water at about 5 miles per hour. That is the boat's speed limit relative to the water it sits in. Now the river itself starts flowing. 10 miles per hour, 20, 50. The boat, with its little motor still humming along, is suddenly moving across the ground at 55 miles per hour. The motor is not working harder. The river is doing the work. The boat obeys its own speed limit, while the water carries it past cliffs and trees at impossible speeds. Space, in Einstein's universe, behaves like that river. It has a current. It can stretch. It can squeeze. It can flow. We know this because we can watch it happening. Astronomers use a tool called redshift to measure how distant galaxies are moving. When light from a galaxy stretches toward the red end of the spectrum, the galaxy is receding. The farther away the galaxy, the faster it recedes. In the 1920s, Edwin Hubble discovered a strange pattern. The most distant galaxies seemed to be moving away faster than light should allow. They were not travelling through space faster than light. Space itself was expanding between us and them. Every cubic inch of empty space was quietly stretching, pushing galaxies apart like raisins in a loaf of rising bread. The bread expands. The raisins stay put relative to their own dough, but the distance between any two raisins grows faster and faster the more bread sits between them. This is confirmed science. The expansion of the universe is measured every day by telescopes around the world. Space flows, space stretches. Einstein's rules forbid objects inside space from crossing the light barrier. The rules say absolutely nothing about space doing the crossing. Alcubierre's warped Proxima Centauri in days instead of centuries. The engine that makes this possible would not be a rocket nozzle. It would be a generator that produces an intense gravitational field shaped in a very specific way, contracting in front, expanding behind, holding a stable pocket in the middle. The math demands precise control over the curvature of space-time at every point on the bubble's surface. That kind of control over gravity is beyond anything human engineering has ever achieved. We can barely detect gravitational waves. We cannot generate them at will. Creating a warp bubble would require a level of mastery that might take centuries to reach. And even then, the negative energy problem waits at the door, daring anyone to cross the threshold. When Alcubierre's paper landed in 1994, most physicists congratulated him politely and filed the idea under charming impossibilities. The reason was a single phrase buried in the math: negative energy density. The warp bubble needed it to exist. Without it, the whole elegant shape falls apart. Space refuses to contract in front of the ship the way the drawing requires. The bubble collapses before it forms. The ship goes nowhere. Positive energy is what fills our universe. Every photon, every atom, every heartbeat carries it. Energy has mass, thanks to Einstein's famous equivalence, and mass pulls things together through gravity. Gravity is what lets planets orbit and stars burn. Negative energy does the opposite. It pushes, it repels. Instead of a bowling ball sinking into a trampoline, imagine a bowling ball that lifts the trampoline up around it. A hole in the floor of reality. For decades, physicists assumed this was purely mathematical fiction. The universe would never let such a thing exist in any meaningful amount. A ghost in an equation, nothing more. Then a Dutch physicist named Hendrik Casimir calculated something strange in 1948. Take two metal plates, polish them to perfect smoothness, hold them incredibly close together in a vacuum, a few thousandths of an inch apart. According to quantum mechanics, empty space is never really empty. It seethes with particles flickering in and out of existence, too fast to catch. Between the plates, only certain tiny particle wavelengths fit. Outside the plates, every wavelength fits. More quantum activity outside than inside. The imbalance creates a measurable pressure, pushing the plates together, and crucially, the energy density in the narrow gap between them is less than the energy density of ordinary empty space, less than empty, negative by comparison. The Casimir effect was measured for real in 1997 by an American physicist in Los Alamos, using plates coated in gold. The force matched the prediction within 1%. Negative energy density was not fiction anymore. It was sitting on a laboratory bench in New Mexico. The celebration lasted about a minute. Then the engineers ran the numbers for a warp drive. Alcubierre's original bubble, scaled to carry a small spacecraft, would require negative energy equal to roughly the mass of the planet Jupiter, converted entirely into negative energy form, held stable in a thin ring around the ship, forever. The Casimir effect between two plates produces a negative energy amount so small that to gather enough for a Jupiter mass conversion, you would need a stack of plates covering the surface of a continent, nested closer than any manufacturing process can achieve. The gap between dream and reality was roughly 30 orders of magnitude, a trillion times more energy than any lab could produce. Physicists called this the energy catastrophe. The warp drive worked on paper. It demanded a power source that did not exist and might never exist. Some argued it never could exist. Quantum field theory put strict limits on how much negative energy can be concentrated in one place for any length of time. The universe seemed to police this loophole ferociously. For 20 years, the Alcubierre drive sat in that purgatory. Too beautiful to forget, too expensive to build. Then a young physicist at NASA, working on a shoestring budget in a back room in Houston, refused to let it die. Harold White works out of a building most people at NASA have never entered. The Eagleworks laboratory sits on the grounds of the Johnson Space Center in Houston, tucked into a wing usually reserved for testing ordinary rocket parts. Inside, the equipment looks more like a physics graduate student's thesis project than a government research program. Vacuum chambers, laser interferometers, a few benches of carefully shielded electronics. The lab's official name is the Advanced Propulsion Physics Laboratory. Its unofficial mission is to do research that mainstream aerospace companies will not touch. White and his small team have spent years asking a question most engineers consider taboo. Can we build a warp drive? And if not a full one, can we at least see whether the physics that underpins one shows up on a laboratory scale? White read Alcubierre's paper as a young researcher and never stopped thinking about it. In 2011, he published a modification. He reshaped the original warp bubble geometry. Instead of the flat ring Alcubierre had drawn, White proposed a thicker, curved ring, like changing a thin wedding band into a fat donut. The new shape still worked mathematically, and by his calculation the energy requirement dropped from the mass of Jupiter to the mass of a large truck. This was the first dramatic cut to the warp drive bill. A truck's worth of negative energy is still impossible with current technology. It is also 9 planets worth of improvement over the original. White's team started running small experiments to look for signs that controlled energy fields could produce any measurable distortion in space itself. They built what they called a White-Jude interferometer. A laser is split in two. The two beams travel through slightly different regions of space. Then they recombine. If space in one region has been subtly warped by a nearby energy field, the beams arrive slightly out of sync. The pattern of light and dark stripes where they meet shifts. In 2013, the lab announced early results. The beams had shifted slightly when the test apparatus was energized, a hint possibly of space-time curvature produced by something other than a planet or a star. The signal was tiny. Critics immediately proposed ordinary explanations: thermal vibrations, air currents, electromagnetic interference. White acknowledged all of them. The experiment was not conclusive proof. It was a breadcrumb, a suggestion that the universe might let this happen. Mainstream physics pushed back hard. Several prominent theorists argued the experiment could not possibly be detecting a real warp effect. The energies involved were trillions of times too small. Whatever the interferometer picked up, they said, had to be noise. White kept going. His lab received modest funding from NASA year after year, not to build a working warp drive, but to keep investigating the foundations. His work was joined by theorists at other universities who began proposing alternative bubble geometries, each one demanding less exotic energy than the last. Then came an accident. In 2021, White's team was running an entirely different experiment. They were studying Casimir cavities, those tiny gaps between polished metal plates, looking for new ways to produce negative energy for other applications. They built a custom array of pillars at the nanoscale and simulated the energy field around it. The simulation produced a shape neither of them expected, something that looked exactly like a miniature warp bubble. For most of its life, the warp drive had one fatal flaw. The energy it demanded had to be negative, exotic, never before produced in useful quantities. Every path forward crashed into that single wall. In March of 2021, a young physicist named Eric Lentz at the University of Göttingen in Germany posted a paper that changed the conversation. Lentz had been working on an ordinary doctoral project involving dark matter. He spent his evenings on a different puzzle. He wanted to know if the warp bubble could be reshaped in a way that required only positive energy. The kind of energy that exists everywhere in the universe, the kind we already know how to collect. He approached the problem from an unusual angle. Instead of assuming the warp field had to carry matter at its core, he treated the entire structure as a kind of soliton, a self-reinforcing wave that holds its shape as it moves, the way a perfect ocean roll can travel for miles without breaking. Solitons appear in many branches of physics. Tsunami waves, certain laser pulses and ripples on deep water all behave this way. Lentz sketched out a warp bubble that was essentially a soliton of curved space. Its shape was different from Alcubierre's original, smoother, rounder, more like a bell than a ring. And when he solved Einstein's equations for this new geometry, the negative energy requirement vanished. The math said a warp bubble could exist using only conventional positive energy. The paper landed in the journal Classical and Quantum Gravity, the same publication that had printed Alcubierre's original work 27 years earlier. The physics community took notice. This was the first time anyone had written down a complete warp solution that did not rely on a substance nobody could produce. The energy bill, however, was still astonishing. Lentz estimated that moving a small spacecraft, about the size of a shipping container, at the speed of light would require an amount of energy comparable to several hundred times the mass of the planet Jupiter. Converted into raw power, the total energy output of human civilization across thousands of years. Critics pointed out this number made the design practically useless. You cannot build a star drive that needs more energy than all the stars in several galaxies. Lentz agreed. He argued his result was not a blueprint. It was a proof of concept. For the first time, positive energy warp drives were shown to be allowed by the laws of physics. The engineering question shifted from "is this even possible?" to "how do we bring the energy requirement down?" Other theorists piled on. Within a year, new papers appeared with refined geometries. Some reduced the energy demand by further factors of thousands. One particularly clever design, published by a small team in 2022, proposed nested warp bubbles, each cancelling part of the energy load of the next. On paper, the numbers kept shrinking. The wall that Alcubierre hit in 1994 had been breached. Not broken, breached. A tunnel through the mathematical obstacle, still blocked by an engineering obstacle of monstrous size, but tunneled through nonetheless. And then, almost exactly as Lentz's paper circulated, two other physicists were quietly preparing a result that went further. They would publish it in 2024, and it would force the physics world to look at warp drives with fresh eyes once more. Alexei Bobrik and Gianni Martir did not meet at a university. They met at a small company called Applied Physics, a private research outfit founded specifically to work on foundational problems in gravity and propulsion. Bobrik came from an astrophysics background. Martir came from entrepreneurship. They split the rent on a tiny office and started writing papers together. In 2021, they published a broad survey of every warp drive proposal ever written: Alcubierre's original, White's modifications, Lentz's positive energy solution, several obscure designs from Russian and Japanese physicists. They fed all of them into a single unified mathematical framework. The results surprised even them. They showed that warp drives form a whole family of possible space-time geometries, not just the one Alcubierre had drawn. Some members of the family travel below light speed, some at light speed, some faster, some use positive energy, some use negative energy, some are spherical, Some are stretched into cigar shapes. The framework gave physicists a catalogue. For the first time, warp drive research had a map. Then in 2024 they went further. Bobrick and Martyr published a new paper describing what they called physical warp drives. The key word was physical. Previous warp drives were beautiful pieces of math that did not always correspond to any actual arrangement of matter and energy you could ever build. The equations worked. Turning them into a real machine was another matter entirely. Bobrick and Martyr produced a warp drive solution using only normal matter. No exotic negative energy. No mysterious quantum effects. A shell of ordinary mass, arranged in a specific geometric pattern, could in principle produce the curvature needed to move a ship at very high speeds. Not faster than light in this particular design, but close to it, using only materials we already know how to build with. The speed limitation was not a setback. It was a foothold. A warp drive that works below light speed but above anything rockets can achieve still collapses interstellar travel times. A ship capable of reaching half the speed of light could reach Proxima Centauri in about 8.5 years. Not 4,000, not 40,000, less than a decade. The shell would need to be extraordinarily dense. Martyr compared the required mass to a small neutron star, the collapsed core of a dead giant star. Packing that much mass into a ship-sized object was obviously not possible with any current engineering, but the principle had been demonstrated. A warp drive could exist without any exotic ingredients at all. The paper also contained a quieter result that physicists found deeply unsettling. Bobrick and Martyr showed that certain configurations of their physical warp drive could be scaled down. A tabletop version. Something you could build with a vacuum chamber and the right kind of energy field. The tabletop warp drive would not carry a ship anywhere. It would be a tiny, fleeting distortion of space, a proof that the underlying physics worked. The experimental equivalent of the Wright brothers' first 12-second hop above a sandy beach. That idea ignited a quiet race. A handful of laboratories around the world began designing experiments to look for exactly this signature. One of them announced later in 2024 that they might have already seen it. Harold White's lab at Eagleworks had spent years studying Casimir cavities. In 2021, one of their simulations returned a result that stopped the team cold. They had been modelling a new kind of Casimir geometry, a custom array of tiny pillars, each smaller than a bacterium, arranged in a precise three-dimensional pattern inside a vacuum chamber. The goal was to measure how much negative energy density the pattern could sustain, exotic materials research, nothing to do with warp drives directly. The simulation calculated the energy distribution around and between the pillars. When White's team plotted the results in 3 dimensions, they saw something they had not expected. The pattern looked exactly like the energy shell of a miniature Alcubierre warp bubble. Positive energy in a specific ring, a pocket of negative energy inside. The geometry matched the theoretical prediction so closely that the team initially assumed a software error. They rechecked. They ran the simulation again with different parameters. The bubble-like structure persisted. They consulted outside theorists, including physicists who had worked on the original Alcubierre math. The consensus was cautious but unmistakable. The simulated energy field had the signature of a warp geometry, scaled down to microscopic size. White and his co-author, the physicist Jerry Vera, published the result in the European Physical Journal C in August of 2021. They called it a nanoscale warp bubble. They were careful not to claim they had built a working warp drive. They claimed very precisely that their Casimir cavity appeared to produce the mathematical shape of 1. The scientific reaction was mixed. Some physicists dismissed the result as a coincidence of geometry. 2 different equations, they argued, can produce similar-looking plots without describing the same physical phenomenon. Others took the finding more seriously. A third camp demanded experimental verification. Simulations are only as good as their assumptions. A real experiment in a real vacuum chamber would settle the question. The Eagleworks team began building that experiment. Progress was slow. The required manufacturing precision pushes the limits of what nanoscale fabrication can currently achieve. Each pillar has to be etched to within a fraction of a single atom's width. The vacuum has to be better than interstellar space. The electronics have to measure energy fluctuations so small they approach the quantum noise floor. Meanwhile, a separate team at Limitless Space Institute, a private research foundation funded by an American aerospace entrepreneur, began building a parallel experiment using a different Casimir geometry. A group in South Korea announced similar work. A laboratory in Italy produced its own variation. The race was on. Not to build a warp drive large enough to carry a spacecraft, but to produce for the first time a measurable fingerprint of a warp-like space-time distortion in a controlled laboratory setting. If any one of these experiments succeeds, the result would be historic. A direct observation of human-made space-time curvature beyond the tiny effects produced by ordinary masses. It would turn the warp drive from pure theory into the earliest stage of applied physics. Mission planners on deep space projects have started watching these experiments carefully. The success of a nanoscale warp bubble would not build a starship. It would prove the starship's engine is not forbidden. And the next question becomes even stranger. If space can be warped, can it also be folded? Every galaxy map in every classroom shows space as a smooth, stretched sheet. Stars are dots scattered across the surface. Distances are straight lines drawn between them. Now imagine folding that sheet in half. Two dots that were 1,000 miles apart on the flat sheet might suddenly sit a fraction of an inch apart once the sheet is folded. Poke a pencil through the paper at the fold, and you have connected them. The pencil's path is the shortcut. The long distance along the surface still exists. The pencil simply does not travel it. Physicists call this kind of shortcut a wormhole, a tunnel through a fold in space itself. The idea first appeared in 1916, scribbled into notes by the Austrian physicist Ludwig Flamm. He was studying Einstein's brand new general relativity equations. Solutions describing black holes turned out to have a mirror image. For every black hole, the math permitted a white hole, a region spewing matter outward. Flamm noticed that two such solutions could, in principle, be stitched together, a tunnel connecting them through a fold in spacetime. Einstein and his collaborator Nathan Rosen picked up the idea in the 1930s. They described the structure more carefully. For decades it was called an Einstein-Rosen bridge. It sat in textbooks as a mathematical curiosity. Nobody took it seriously as a travel method. The physicist John Wheeler rechristened the concept in the 1950s. He called them wormholes. The name stuck because the picture it evokes is exactly right. An apple has a long path along its skin from top to bottom. A worm chews a tunnel straight through the core. Same two endpoints, radically shorter journey. Mathematically, wormholes are allowed by general relativity. The equations do not prohibit them. Space can fold, space can stretch, space can tunnel. A pair of wormhole mouths, one on Earth and one near a distant star, could connect regions of the universe separated by trillions of miles. Step through one mouth, emerge from the other. Your journey takes seconds. Light itself, travelling the long way around through normal space, would take years to make the same trip. A wormhole does not break the speed of light any more than a warp drive does. Inside the tunnel, light itself still moves at its constant pace. The trick is that the tunnel is much shorter than the external distance. Light crossing the tunnel gets there quickly because the tunnel itself is short. A traveller in the tunnel does the same. Speed limit respected. Arrival time obliterated. The idea is confirmed as mathematically possible. The reality of constructing one or finding one is a different problem. Wormholes, if they exist naturally, would likely be microscopic. The foamy structure of space-time at the quantum scale may already be riddled with them, popping in and out of existence faster than any instrument can detect. Useful wormholes, the kind you could fly a ship through, would need to be enormous. Miles wide at the mouth, stable, open, traversable without shredding whatever enters. And that is where the mathematics turns cruel once again. A natural wormhole, the kind that would form on its own in the universe's early chaos, collapses the moment anything tries to pass through it. The tunnel pinches shut. The traveller is crushed before they reach the far side. To keep the tunnel open, something has to prop up the walls. Something strange. A natural wormhole behaves like a soap bubble stretched too thin. The same gravity that curves space-time enough to open a tunnel also tries to close it. The geometry is inherently unstable. Any disturbance, any packet of matter or energy entering the throat tips the balance. The tunnel constricts. The walls rush inward at the speed of light. Physicists modelled this collapse in detail in the 1970s. Kip Thorne, a gravitational physicist at Caltech, ran the numbers for a theoretical traveller trying to cross a standard Einstein-Rosen bridge. The results were grim. By the time the traveller reached the midpoint, the throat had already begun to close. The walls would meet at the traveller's position. The crossing would compress the traveller into an infinitely small point, a death at the core of a black hole, essentially, disguised as a shortcut. The math was airtight. A wormhole left to its own gravitational forces cannot be traversed. It opens and closes faster than any signal, any probe, any ship can cross it. For the wormhole to survive a crossing, its throat has to be held open, propped in effect against the tendency of gravity to pinch it shut. Ordinary matter cannot do this. Ordinary matter always attracts. More mass in the tunnel's walls only makes the walls collapse inward faster. The only way to keep the walls apart is to fill them with something that pushes outward, something whose gravity repels instead of attracts. Exotic matter, as the field now calls it, with negative energy density and a strange property called negative pressure. Kip Thorne, along with his student Michael Morris, wrote the defining paper on this problem in 1988. They proved a mathematical theorem. A traversable wormhole, stable enough for a spacecraft to cross, must contain exotic matter. No exceptions, no clever workarounds. The physics demands it. Their paper included a second finding, almost as striking. The amount of exotic matter required scales with the size of the wormhole. A microscopic wormhole, perhaps the size of a single atom, would need only a tiny sliver of exotic matter. A wormhole wide enough to pass a spacecraft through would require vastly more. Thorne estimated that keeping a wormhole mouth just a few miles wide open long enough for a ship to cross would need exotic matter equivalent in mass to the planet Jupiter. The Jupiter problem returned, in a different costume. Worse still, the exotic matter needed to hold the throat open could not be any ordinary collection of mass. It had to be distributed in precisely the right pattern, wrapped around the throat, held in place by forces nobody has yet described. The engineering picture, even assuming the raw material could be produced, stretches beyond any current framework. Some physicists began asking whether the exotic matter could be avoided entirely, whether a different kind of wormhole solution existed. A paper in 2017 by a team at Harvard and Stanford proposed a clever workaround using entanglement between two black holes. The arrangement, they argued, could create a kind of usable wormhole without exotic matter. The catch was that any signal sent through it would arrive slower than a signal sent by ordinary light through normal space. Useful for some experiments, useless for travel. The search continued, and the place most physicists looked for hope was the Casimir effect, the same quiet phenomenon that had given the warp drive its first crack of sunlight. The Casimir effect sits at the strange edge of physics. It is small. It is real. It is the only laboratory-confirmed source of negative energy density that humans have ever produced. The setup that makes it happen could fit on a dinner plate. Two flat metal surfaces, polished until no atomic irregularity larger than a few nanometers remains, suspended face-to-face in a sealed vacuum chamber. Less than 1/10,000th of an inch separates them. The air has been pumped out. No gas molecules exist between the plates. No light. No photons of ordinary kind. What should be empty? It is not empty. Quantum field theory, the deepest theory of matter humans have, says empty space is a roiling ocean. Particles of every kind, from photons to electrons to ghostly things called virtual particles, constantly appear and disappear. They borrow energy from the vacuum itself, exist for the briefest flicker of time and vanish again. The flicker is so fast that no ordinary measurement can catch it. But the average effect is measurable. It gives empty space a background hum of activity. Between the two Casimir plates, only certain wavelengths of this quantum activity fit. The gap is so narrow that larger wavelengths get excluded. Outside the plates, the ocean churns normally. Inside, a quieter version of the ocean exists. Fewer virtual particles, less background energy. The quantum activity inside the gap is measurably lower than the activity in the rest of the vacuum. Lower than empty, by comparison, negative. The Dutch physicist Hendrik Casimir predicted this in 1948, doing calculations on a napkin while discussing quantum physics with his colleague Niels Bohr. He worked out that the pressure difference should push the plates together with a tiny but measurable force. The experiment required 50 years to perform cleanly. In 1997, Steve Lamoureux at Los Alamos National Laboratory pulled it off. He measured the Casimir force between gold-coated plates and matched Casimir's prediction within 1%. The ghost was real. Negative energy density existed, sitting quietly inside laboratory equipment on a bench in New Mexico. The celebration was short, for the same reason it had been short the first time. The amount of negative energy per plate was absurdly small, measured in quintillionths of a joule. To produce enough to hold open a wormhole large enough for a spacecraft, you would need to tile a surface larger than several planets, with these tiny gaps, stacked in layers, nested within layers, to a depth that no known engineering technique could achieve. The gap between what nature allows and what engineering can deliver was 30 orders of magnitude, a number so large it has almost no meaning in ordinary experience. Imagine needing to count every grain of sand on every beach on Earth, and then doing that task a trillion times. Still, the point had been made. Nature does produce negative energy. The universe is not forbidding it. The warp drive theorist and the wormhole architect both had at minimum a seed. A proof that the universe permits the key ingredient, even if only in whispers. The next step was to scale the whisper into a roar. Physicists began exploring whether stronger Casimir-like effects could be produced with different geometries, different materials, different boundary conditions, and while they worked, another team returned to the original wormhole design with a new strategy entirely. Kip Thorne did not start his career looking for shortcuts through space. He came to the wormhole problem sideways, through a favour to a friend. In 1985, the astronomer Carl Sagan was finishing a novel called Contact. The book involved a protagonist travelling to a distant star system. Sagan wanted his fictional travel method to be grounded in real physics. A black hole he had initially written. He called Thorne, then the leading expert on black holes at Caltech, to check the details. Thorne ran the math. He told Sagan that a black hole would not work. Anything entering a black hole gets crushed to infinite density before reaching any destination. Sagan's plot was physically impossible. Then Thorne did something most physicists would not have done. He asked himself what would work. What kind of space-time geometry would let a human cross interstellar distances quickly and survive? He set his graduate student Michael Morris to work out the answer. What emerged, over the next 3 years, was the first serious engineering blueprint for a traversable wormhole. Morris and Thorne started from the desired end state. A human must be able to enter one mouth of the wormhole, travel through, and emerge from the other mouth alive. No crushing, no roasting, no time dilation mishaps so severe that the traveller dies of old age during the crossing. The geometry had to be gentle enough for ordinary flesh to survive. They reverse-engineered the equations. They derived the exact shape of space-time that would produce those conditions. The result was a wormhole throat shaped like a smooth hourglass, wider in the middle than at the mouths, with carefully tuned curvature at every point. The paper they published in 1988 in the American Journal of Physics was a milestone. For the first time, a wormhole had been described not as a mathematical curiosity, but as an object with engineering specifications. The paper listed requirements: minimum throat width, maximum curvature, exotic matter distribution, tidal force limits. It read, in places, like an industrial design document for a structure that could not yet be built. Their conclusions were stark. A wormhole safe for human travel would need a throat at least several miles wide. The exotic matter required to hold it open, if concentrated in a thin shell around the throat, would weigh as much as the planet Jupiter. The alternative was to spread the exotic matter over a wider region, lowering its density but increasing the total volume required. More importantly, Morris and Thorne addressed a possibility that had haunted wormhole research from the start: time travel. If one mouth of a wormhole moves rapidly while the other stays still, the difference in their local times could, in principle, allow messages or even travellers to arrive before they departed. Their paper acknowledged the problem. They did not resolve it. They simply noted it. The paper lit a fire. Dozens of physicists began proposing variations on the Morris-Thorne geometry. Some tried to reduce the exotic matter requirement. Some tried to find geometries that avoided the time travel problem. Some tried to use the Casimir effect as a miniature power source. The blueprint existed. The building materials did not. And while wormhole research slowly matured, an entirely different kind of faster-than-light trick was showing up in laboratories at a much smaller scale. Quantum mechanics has a habit of violating common sense. Some of its strangest violations happen at the smallest possible scales, in ways that force physicists to reconsider what motion itself means. One of those violations is called quantum tunneling. A single particle, something like an electron or a photon, approaches a barrier. The barrier is an energetic hill. In ordinary physics, the particle either has enough energy to climb over the hill, or it does not. If it lacks the energy, it stops, it bounces back. The hill is a wall. Quantum mechanics refuses this logic. A particle that does not have enough energy to cross the barrier can still, sometimes, appear on the other side. It did not climb the hill. It did not go around it. It tunneled through, as if the wall briefly ceased to exist. This is confirmed physics. Scanning tunneling microscopes, one of the most important tools in modern science, work because of this effect. They measure current that flows through a tunneling gap between a sharp tip and a surface. Every smartphone chip relies on carefully managed tunneling. Nuclear fusion inside stars, including our own, happens because protons tunnel through the electrical repulsion that should keep them apart. Tunneling is real, it is harnessed, it is understood, and it raises a deeply unsettling question. How long does the tunneling take? If a particle tunnels across a barrier, it spends some amount of time inside the barrier. How much time? In the 1980s, physicists started measuring it. The answer was confusing. The tunneling time appeared to be much shorter than the time light would take to cross the same distance in empty space. Some experiments, conducted by the German physicist Günther Nimtz in the 1990s, seemed to show photons tunneling across barriers at speeds that mathematically exceeded the speed of light. Nimtz became convinced he had broken Einstein's limit. He performed his most famous experiment in 1995. He encoded a short musical phrase, the opening of a Mozart symphony, onto a microwave beam. He sent the beam across a tunneling barrier. Some of the photons passed through normally. A small fraction tunneled. Nimtz measured their arrival times. The tunneled photons appeared to arrive sooner than photons that had crossed the same distance in ordinary space. He calculated their effective speed at roughly 4 times the speed of light. The physics community exploded into argument. Had Nimtz really broken the cosmic speed limit? Could information travel faster than light? The answer, after years of careful analysis, was more subtle than either side had expected. Nimtz's photons had indeed appeared to travel faster than light in a certain technical sense. But the information carried by the signal, the pattern that could actually be used to communicate, did not. The leading edge of the wave contained no decodable content. By the time enough of the signal had arrived to reconstruct the music, the average arrival time had slowed to below light speed. Einstein's limit, many theorists argued, had survived. Tunneling seemed to cheat the rules only at the surface. At the level of information, the speed of light still ruled. But the argument was not over. Some physicists still believe Nimtz's experiments revealed a loophole that has been papered over by semantic definitions. The controversy persists to this day, a quiet feud inside the foundations of quantum mechanics. Günther Nimtz never accepted the verdict that tunneling respects the speed of light. He spent the rest of his career, until his death in 2022, defending his experiments and running new ones. The setup was elegant. A microwave signal, generated by an ordinary lab source, was split into 2 paths. One path travelled through open space in the laboratory. The other path passed through a carefully constructed barrier, typically a waveguide designed to block microwaves of that exact frequency. The barrier was a mathematical wall. The signal should not have been able to cross it. Some of the signal crossed anyway. Quantum tunneling let a small fraction of the microwave photons appear on the far side. Nimtz's genius was in the timing. He measured with picosecond precision when the tunneled signal arrived compared to the untunneled signal. The tunneled signal consistently arrived earlier. Not by much, enough to matter. Nimtz encoded Mozart's 40th Symphony onto the microwave carrier and sent it across the barrier. The tunneled copy reached the detector ahead of schedule. The music was garbled slightly. It was still recognizable. Nimtz and his collaborators published a paper claiming faster-than-light transmission of meaningful information. The response from the mainstream physics community was sharp. Several theorists, led by Ephraim Steinberg at the University of Toronto, argued that Nimtz had been fooled by a subtle property of wave physics. The leading edge of any wave pulse contains almost no energy and almost no detectable information. A tunneling barrier selectively lets through the leading edge while blocking most of the main body of the pulse. The result is a signal that appears to arrive early because only its front edge survives. The bulk of the information, the part you would actually decode to hear the music, arrives at normal speed or slightly slower. In this view, Nimtz was not transmitting Mozart faster than light. He was transmitting a pre-existing hint of Mozart, already contained in the front edge of the pulse before the main signal arrived. No cosmic speed limit had been broken. Nymphs disagreed, pointedly. He argued that his detectors were measuring the actual reconstructed signal, not just the leading edge. He accused his critics of redefining the concept of signal arrival to preserve Einstein's limit at all costs. He ran new experiments with different encoding methods. Each one seemed, to him, to confirm the original result. The debate never fully resolved. Nymphs' work passed peer review. His experiments were reproduced in other laboratories. The measurement of tunneling times was not in dispute. What remained in dispute was the interpretation. Did tunneling constitute faster-than-light information transfer, or a clever illusion of one? Modern measurements have continued to refine the question. In 2020, a team at the University of Toronto used ultra-cold rubidium atoms to measure tunneling times with extraordinary precision. The team reported that the average tunneling particle spent less than a millionth of a second inside the barrier. That was shorter than classical physics would have predicted, though consistent with quantum calculations. Crucially, the team emphasized that their result did not imply faster-than-light signaling. The question of what tunneling actually means for information transfer remains one of the most contested topics in quantum mechanics. The wall around the speed of light bends, it warps, it shudders under careful experimental pressure. Whether it truly breaks, at the level of something we could use to send a message to another star, remains for now an unsolved mystery. The physicists who argue quantum tunneling respects the speed of light have a simple point. A loophole you cannot use to send a message is not a loophole at all. Signal speed, in modern physics, is defined very carefully. It is the speed at which new information can be transmitted from one place to another. A tunneling particle may appear to arrive ahead of a photon that travelled the same distance through empty space. But the tunnelled signal contains no information that was not already predictable from the leading edge of the original pulse. The receiver could have guessed the content before the signal finished arriving. The apparent speed-up is the consequence of a guess, not a transmission. This is the heart of the debate. Can you use quantum tunneling to actually communicate? Not to shuffle around a pre-existing waveform, but to send a genuinely new piece of information that could not be predicted in advance. Experiments have repeatedly answered no. A team at the Weizmann Institute in Israel tested this directly. They designed a tunneling experiment in which they injected genuinely unpredictable data into the signal, random bits generated by a quantum source. If tunneling could transmit new information faster than light, the random bits should have arrived early. They did not. The tunneled signal conveyed the random data at exactly the speed of light, or slower. The leading edge of a pulse, they showed, cannot be manipulated to carry new information faster than light. The quantum statistics simply forbid it. Nature has a subtle rule built into the foundations of quantum mechanics. You can play games with where a particle is detected. You cannot play games with what a particle tells you. Theoretical physicists have formalized this rule as the no-signaling theorem. It is one of the deepest results in modern physics. The theorem proves that no quantum effect, including tunneling, entanglement, or any other spooky phenomenon, can be used to send a usable message faster than light. The proof is airtight. It uses the same mathematics that underlies the standard model of particle physics, the framework that has predicted every particle experiment of the past 50 years with astonishing accuracy. For many physicists, this settles the matter. Nymphs' Mozart experiments, however striking, cannot be turned into a telephone line to the stars. The apparent speed-up vanishes the moment you try to use it. A minority of researchers continues to push back. They argue the no-signaling theorem depends on assumptions that may not hold in every physical situation. They propose exotic regimes, extremely strong fields, curved space-time near black holes, or quantum systems coupled to gravity, where the theorem might fail. No experiment has ever demonstrated such a failure, but the theorists keep looking. The practical consequence for a mission planner is clear. Quantum tunneling is real, confirmed and useful for many technologies. It is almost certainly useless for interstellar communication. A starship crew cannot call home by tunneling their radio signals through a barrier. The message arrives at light speed, same as always, which means the speed of light still rules for information. It rules for matter. It rules for energy. Every experiment ever performed, in every laboratory on Earth, agrees on this one point. except perhaps for one strange class of particles that physicists have speculated about for nearly 70 years. Particles that, if they exist, would never have travelled slower than light even for a single instant. In 1967, the physicist Gerald Feinberg at Columbia University published a paper with a deceptively simple title. He called it "On the Possibility of Faster-than-Light Particles." The content was anything but simple. Feinberg asked a question that had been hovering around the edges of physics for decades. Einstein's theory forbids ordinary particles from crossing the speed of light, because doing so would require infinite energy. But what about a particle that started out faster than light? A particle that was born on the wrong side of the cosmic speed limit and could never slow down below it. The math turned out to be surprisingly consistent. If such a particle existed, it would obey its own strange rules. Its mass would be imaginary in the mathematical, and a theoretical minimum of light speed it could never drop to. The two worlds would mirror each other across the light barrier, neither able to cross into the other's territory. The consistency of the math was striking. Tachyons obey energy conservation. They obey momentum conservation. They respect most of the symmetries physicists care about. On paper, a universe with tachyons in it looks almost as orderly as a universe without them. The problem is that tachyons raise hair-raising questions about causality. If a tachyon travels from one place to another faster than light, then in some reference frames, it would appear to arrive before it left. An observer flying past the experiment at high speed would see the tachyon emerge from the receiver before it entered the transmitter. Effect before cause, output before input. Some physicists argued this was a fatal flaw. If tachyons allow signals to arrive before they were sent, they could be used to send information into the past. Paradoxes would follow. Grandmothers, telegraph machines, the whole familiar menagerie of time travel contradictions. Others argued the contradictions could be avoided if tachyons were forbidden from carrying information. A tachyon might exist as a fleeting wave, unable to be harnessed for communication. Its speed could be real, its usefulness would be zero. The deeper question was whether tachyons existed at all. Feinberg did not claim they did. He asked only whether they could. His paper opened a hunt that continues to this day. Several experiments over the past half-century have searched for tachyon signatures. Everyone has come up empty, or almost empty. Tachyons, if they exist, should leave a fingerprint. Faster-than-light particles would interact with ordinary matter in distinctive ways. They would emit a specific kind of radiation as they crossed the boundary between vacuum and medium, a reverse of the well-known Cherenkov glow that ordinary fast particles produce in water. They would trigger specific patterns in particle detectors. They would alter the arrival times of signals from distant astronomical events. Starting in the 1960s, physicists began looking for these fingerprints. The earlier searches used primitive detectors and came up with nothing. The results were not surprising. Tachyons, if they existed, would be rare, hard to catch, and difficult to distinguish from ordinary particles moving at high speed. In the 1970s, a team in Australia tried a different approach. They analysed cosmic ray data. Cosmic rays are high-energy particles from deep space that rain down on Earth constantly. The team looked for particles arriving earlier than any ordinary particle could. If a tachyon had been produced by a distant supernova, for example, it should reach Earth before the light from the same event. The search found hints, but nothing conclusive. A few anomalous early arrivals appeared in the data. None of them could be pinned down as definitively tachyonic. Conventional explanations, measurement errors, or unusual atmospheric effects could account for every signal. In 1987, a supernova exploded in the Large Magellanic Cloud, a satellite galaxy close to our own. It was the brightest supernova observed from Earth in nearly 400 years. Astronomers detected neutrinos from the blast about 3 hours before the visible light arrived. For a brief moment, some theorists wondered if the neutrinos had travelled faster than light. The explanation turned out to be mundane. The neutrinos left the supernova earlier than the photons. They escaped from the dying star's core directly, while the light had to work its way out through layers of stellar material. Both travelled at essentially the speed of light across the intervening space. The neutrinos arrived first because they started earlier, not because they moved faster. No tachyons, no broken physics. More modern searches have continued. In 2011, a team working with the Opera experiment in Italy announced what appeared to be a measurement of neutrinos travelling slightly faster than light, between a particle accelerator in Switzerland and a detector underground in central Italy. The result made headlines around the world. For several months it seemed possible that tachyons had finally been caught in a laboratory setting. The announcement collapsed 6 months later. A loose fibre optic cable in the timing system had introduced a delay of about 60 nanoseconds. Once engineers fixed the cable and reran the experiment, the neutrinos arrived at exactly the speed of light. The earlier result was an equipment error. No faster-than-light travel had occurred. Every serious search for tachyons has ended this way. A tantalizing hint, followed by a careful investigation, followed by a mundane explanation. The current verdict is that tachyons are allowed by the math, but have never been observed. They remain a theoretical possibility. They are not a confirmed feature of our universe. A mission planner cannot yet design a propulsion system around them. Space itself, however, has demonstrated something much stranger. During a brief moment in its infancy, space moved faster than any particle ever could. The early universe did something no particle can do. 13 billion years ago, a fraction of a second after the Big Bang, space itself expanded faster than light. Not by a little, by an enormous factor. In less time than it takes a single electron to complete one orbit around an atomic nucleus, the observable universe grew from smaller than an atom to larger than a grapefruit. The expansion rate during that instant exceeded light speed by a factor that defies easy description. This event is called cosmic inflation. It was proposed by the American physicist Alan Guth in 1980. He was trying to solve several problems that had been nagging cosmologists for years. The universe looked too smooth at large scales. The temperature of the leftover radiation from the Big Bang was almost identical in every direction, even between regions that should never have been in contact with each other if the universe had expanded at a normal rate. How could opposite sides of the sky have reached the same temperature when they had never exchanged any energy? Guth's answer was radical. At the very earliest moment of the universe's history, space underwent a brief period of exponential expansion. Every cubic inch doubled, then doubled again, roughly 100 doublings in a tiny fraction of a second. The inflation ended almost as soon as it began. What had been a tiny patch became the entire observable universe, stretched so rapidly that its original uniformity was preserved across the vast new volume. The inflation rate far exceeded the speed of light. This was allowed because the speed limit applies to objects moving through space. Space itself can expand as fast as it wants. The rule that forbids a rocket from outrunning a photon does not constrain the growth of the vacuum between galaxies. Inflation remains a theory, though a very well supported one. The fingerprint it left in the cosmic microwave background, the faint afterglow of the Big Bang that fills the sky in every direction, matches the predictions of inflationary models with remarkable precision. The subtle ripples in that background are the seeds from which galaxies eventually grew. Their distribution, their size, their statistical properties all agree with what inflation predicted. The significance for interstellar travel is profound. The universe has already demonstrated at its own larger scales that faster-than-light motion is possible if the thing doing the moving is space itself. Every warp drive concept since Alcubierre has leaned on this fact. If the universe did it once, the argument goes, it can do it again, on a smaller scale, with the right engineering. Nobody knows what powered cosmic inflation. The leading hypothesis is a field of energy called the inflaton field, which permeated the early universe and caused the exponential growth through its negative pressure. Negative pressure, the same property required for traversable wormholes, the same property produced in tiny amounts by Casimir cavities. The universe's most fundamental engine of faster-than-light expansion appears to rely on the same ingredient that human engineers would need to build a warp drive. The inflaton field, if it exists, decayed almost immediately after inflation ended. It released its energy into the particles that would become atoms, galaxies, and eventually stars. The field is gone now. Whether it could ever be recreated in a laboratory remains an open question. While physicists debate that, the universe is still expanding faster than light in a quieter way, right now, in every direction you can look. Point a telescope at any random patch of deep sky, and the light you collect has been travelling for billions of years. Some of those galaxies are already, at this very moment, moving away from us faster than light. We see them because the photons they emitted long ago have finally arrived. But if we launched a spacecraft toward them today, we would never catch up. the expansion of the universe is not limited to the first fraction of a second of its history. It continued at much slower rates throughout the entire 13 billion years since. It is continuing right now. Space between galaxies stretches every second, pushing objects farther apart. The more distance that sits between 2 points, the faster they recede from each other, because there is more expanding space between them. For galaxies within roughly 14 billion light-years of us, the expansion rate is slower than the speed of light. Light from those galaxies can still reach us, and light we send could still reach them, given enough time. These are the galaxies in our cosmic neighborhood, gravitationally linked to us by a trickle of photons that can still cross the intervening space. Beyond that distance, the expansion rate exceeds the speed of light. Galaxies farther away are receding from us faster than any signal can travel back. They are inside what cosmologists call the cosmological horizon. A horizon in the same sense as the edge of the world as seen from a ship at sea. We can no longer communicate with them. Anything they did after the moment when their recession rate crossed light speed is forever invisible to us. Any message we send them now will never arrive. The number of galaxies trapped behind this horizon is enormous. Billions of galaxies, each containing hundreds of billions of stars, are already beyond our reach. And every second, more galaxies cross the line. The universe is quietly closing its gates around us. This is not a theoretical estimate. It is measured. The astronomer Edwin Hubble discovered the expansion in 1929. His measurements have been refined ever since. Modern observations using space telescopes and careful surveys place the rate of expansion at about 46 miles per second for every million light-years of distance. That rate is consistent across the sky. The universe is expanding uniformly in all directions everywhere at once. Combined with the acceleration of expansion discovered in 1998, the picture grows darker. The expansion is speeding up. Space is stretching faster now than it was a billion years ago. In the far future, most of the observable universe will drift beyond our horizon. Our descendants, if any survive, will look up at a sky nearly empty of distant galaxies. Only our own local group, bound together by gravity, will remain visible. A mission planner stares at this reality with cold clarity. The universe is shrinking our window. Every star we fail to visit this century becomes slightly harder to visit next century. The math that forbids light-speed travel also dictates that certain destinations are already lost to us, even in principle. A civilization that hopes to explore beyond its own galactic neighborhood has to solve the speed of light problem quickly, or never at all. Which is why claims of impossible drives, even discredited ones, get attention they probably should not deserve. In 1999, a British engineer named Roger Scheuer announced that he had built a propulsion device that violated the laws of physics. His machine was small, a copper cone, roughly the size of a coffee can, sealed at both ends and filled with nothing but microwaves. No propellant, no exhaust, no reaction mass leaving the device in any direction. According to every textbook ever written on rocket propulsion, such a device cannot produce thrust. The conservation of momentum, a law so fundamental that it predates Einstein by centuries, forbids it. For something to push forward, something else must push backward. An engine without an exhaust is an impossibility. Scheuer claimed his cone produced thrust anyway. The microwaves bouncing inside the cavity, he argued, exerted slightly different pressures on the two ends of the cone because of the shape. The narrower end, he said, experienced less radiation pressure than the wider end. The difference produced a net force, a push, thrust from nothing. The physics community was skeptical to the point of open dismissal. Scheuer was not a crank. He had a respectable engineering background. His math, however, appeared to mix up concepts from different frames of reference in ways that many professional physicists considered elementary errors. Critics pointed out that if the M-drive worked, it would violate conservation of momentum, one of the best confirmed laws in all of science. A law confirmed by every particle experiment, every rocket launch, every billiard ball collision ever measured. And yet, Scheuer's prototypes appeared to produce thrust, small amounts, micronewtons or thousandths of a gram of force, barely above the threshold of measurement. He built several versions, refining the design, and each one showed the same tiny push. Other teams tried to replicate the experiment. A Chinese group at Northwestern Polytechnical University in Xi'an announced in 2010 that they had measured thrust from their own M-drive. A A second Chinese team followed, then a group at Dresden Technical University in Germany. Then, most dramatically, a team at NASA's Eagle Works laboratory, the same group working on warp drive experiments in Houston. The NASA announcement came in 2016. Harold White and his colleagues published a peer-reviewed paper reporting that their M-drive prototype produced thrust of about 1.2 millinewtons per kilowatt of input power. The measurements were conducted in vacuum to rule out air currents. The results were statistically significant. The paper appeared in the Journal of Propulsion and Power. If the result was real, it would be the single greatest discovery in physics since Einstein. A propulsion method that required no propellant could push a spacecraft indefinitely, as long as it had electricity. It could run on solar panels. It could accelerate continuously across interstellar distances. Without violating the speed of light, an M-drive-powered ship could reach nearby stars in decades rather than millennia, if the result was real. That caveat hung over the field like a storm cloud. Every independent physicist who examined the experimental setup identified potential sources of error. Thermal effects from the heated copper, subtle electromagnetic interactions with the measurement apparatus, vibrations from the power supply. Each of these could produce apparent thrust that was not actually propulsive. A rigorous test was inevitable. It came, and it came hard. In 2021, a team of German physicists at Dresden Technical University, the same institution that had previously reported positive M-drive results, completed what may be the most careful test of the device ever performed. Their earlier positive result had made them cautious rather than confident. They knew the thrust signal was small. They knew subtle effects could mimic it. They built a new experimental apparatus specifically designed to rule out every known source of systematic error. The new setup was meticulous. They suspended the M-drive on a specialized torsion balance sensitive enough to measure forces equivalent to the weight of a single grain of sand. They placed the entire apparatus inside a high-quality vacuum chamber to eliminate air currents. They used a custom power delivery system that isolated the drive from its electrical supply through carefully designed cables. They ran the experiment with the drive both active and inactive, comparing the results to establish a baseline. When they turned on the microwave power, they measured thrust, a clear, repeatable, statistically significant force. Then they changed the orientation of the drive inside the chamber. The thrust direction should have changed with it. If the M-drive was genuinely producing directional force from the shape of its cavity, rotating the drive should rotate the thrust vector. The thrust direction did not change. The signal stayed aligned with the supporting structure of the apparatus, not with the drive itself. Whatever was producing the apparent thrust was coming from the mounting system, or the electrical cables, not from the copper cone. The force the Dresden team had measured, and that previous teams had also measured, was an artifact of the experimental setup. It was real. It was measurable. It was not propulsion. The team published their result in a respected aerospace physics journal. The paper was thorough, polite, and conclusive. The M-drive does not produce thrust. The earlier positive results were artifacts of heating, electromagnetic effects on the apparatus, or other subtle interactions between the drive and its environment. NASA's Eagle Works team took the results seriously. Subsequent analysis of their own 2016 data, using the error sources the Dresden team had identified, showed that their measured thrust was likely explainable by the same artifacts. The Eagle Works group quietly stopped advocating for the M-drive as a viable technology. Scheuer continued to defend his invention. A handful of private companies, mostly funded by speculative investors, continued to pursue it. Mainstream physics moved on. The M-drive story carries a lesson that mission planners learned the hard way. Anomalous results are not the same as new physics. A signal that appears repeatedly in multiple laboratories may still have a mundane explanation. Extraordinary claims require extraordinary verification, not simply repeated measurement. The laws of thermodynamics and momentum conservation, built up from centuries of careful experimentation, are not easily overturned by a thrust signal of a few micronewtons. The M-drive was a dead end. But it was not the only exotic propulsion concept that caught the attention of serious aerospace agencies. A different device, based on a different theoretical foundation, had been quietly circulating through government research channels for years. It had roots in a dense, almost impenetrable theoretical framework developed by a single German physicist in the 1950s. His name was Burkhard Heim, and his equations were supposed to describe not only gravity and electromagnetism, but also a previously unknown dimension of space-time. Burkhard Heim lived most of his life in near-total obscurity. He spent his days in a small apartment in Northam, Germany, working alone at a desk. A childhood accident during an explosives experiment had left him blind, deaf, and without hands. He communicated through a specialized assistant. Despite those limitations, he produced over the course of several decades one of the most mathematically elaborate theoretical frameworks ever attempted outside mainstream physics. Heim believed he had unified gravity with the other fundamental forces. His theory, which he called Heim theory, proposed that space-time has 6 or 8 dimensions rather than the standard 4. The extra dimensions in his framework were responsible for producing the masses of elementary particles. Heim claimed his equations predicted particle masses with extraordinary accuracy, matching experimental values better than any other theory of the time. Mainstream physicists largely ignored his work. His papers were written in a dense, idiosyncratic style that made them difficult to evaluate. He published primarily in German and often in obscure venues. Most professional physicists who glanced at his work concluded that his methods were unorthodox and his conclusions unverifiable. A small group of researchers, however, took Heim seriously. Among them was an Austrian engineer named Walter Droscher. After Heim's death in 2001, Droscher continued developing the theory. Together with his colleague Joachim Heuser, he pushed Heim's equations in a new direction. If Heim's extra dimensions were real, they argued, they might allow for a new kind of propulsion. Droscher and Heuser published a paper in 2004 proposing a Heim theory-based drive. The concept was exotic. By spinning a superconducting ring at extremely high rotation rates in a strong magnetic field, the drive would, according to the theory, couple to Heim's extra dimensions. This coupling would allow the drive to generate thrust without exhaust. More strikingly, it would allow the drive to enter a higher dimensional mode in which effective speeds far exceeded the speed of light. The paper made specific predictions. A ship equipped with a Heim drive could, in principle, reach Proxima Centauri in about 80 days. A trip to a star 50 light-years away would take about 3 years. The numbers were breathtaking. The paper caught the attention of the American Institute of Aeronautics and Astronautics. They awarded it a prize in 2004 for one of the best papers on future propulsion concepts at their annual conference. The United States Air Force reviewed the proposal and conducted preliminary evaluations. For a few years it appeared that Heim theory might actually be funded for experimental testing. The tests never came. A closer examination of Heim theory by independent physicists identified significant mathematical inconsistencies. The predicted particle masses, on which Heim's reputation rested, turned out to be approximately correct but not as exact as Heim's followers had claimed. The claimed agreements depended on specific parameter choices that could be adjusted to fit almost any data. The predictions were not as predictive as they had appeared. The proposed Heim drive faded from serious consideration. Droscher and Heuser continued to develop their ideas. A small community of enthusiasts still follows Heim theory. Mainstream physics has filed it alongside other unified field theories that could not withstand careful scrutiny. The lesson again was that exotic theoretical frameworks rarely deliver on their most dramatic promises. Real breakthroughs, when they come, tend to arrive through careful extensions of established physics, which is exactly what a different research group began pursuing in the early 2000s, with a proposal that did not break any rules at all. In April of 2016, a Russian billionaire named Yuri Milner stood on a stage in New York City alongside the physicist Stephen Hawking and the inventor Freeman Dyson. Milner announced he was putting $100 million into a project called Breakthrough Starshot. The goal was to send a spacecraft to Proxima Centauri within a human lifetime. The ship would not be a rocket. It would be smaller than a postage stamp. Starshot's concept is disarmingly simple. A tiny chip-sized probe containing cameras, radio antennas, and a compact power source is attached to a reflective sail about 13 feet across. The sail is made of ultra-thin material, possibly graphene or a specialized plastic weighing less than an ounce per square yard. Together, the probe and sail weigh about 1/10 of an ounce. The propulsion comes from the ground. An array of hundreds of ground-based lasers, located in a high, dry location like the Atacama Desert in Chile, would fire simultaneously at the sail. The combined laser beam would deliver 100 gigawatts of power to the sail for about 2 minutes. That 2-minute push would accelerate the probe to 1/5 of the speed of light. About 134 million miles per hour. The fastest object ever sent by humans, faster than any rocket could ever achieve with chemical fuel. After the push, the sail coasts. No fuel to carry, no engine to maintain. The probe drifts through interstellar space at a relentless 20% of light speed for just over 20 years until it enters the Alpha Centauri system. During its brief passage through the target system, it would take photographs, collect data, and beam the results back to Earth. The signals, travelling at light speed, would arrive 4 years later. 24 years after launch, Earth would receive the first close-up images of a planet orbiting another star. Every component of the plan uses known physics. No exotic matter, no warp drives, no wormholes. The speed of a light is respected at every step. The probe goes fast, but not faster than light. The scheme is entirely compatible with Einstein's rules. The engineering challenges are enormous. The sail must survive the laser blast without vaporizing. The probe must function in interstellar temperatures and radiation for decades. The ground-based laser array would need to be roughly 10 times more powerful than any laser system ever built. The chip-sized electronics have to be hardened against cosmic rays that could wipe their memory during the long cruise. But every challenge is engineering rather than physics. Nothing in the Starshot concept demands a new law of nature. The project's scientific advisory board, which includes leading astrophysicists and aerospace engineers from a dozen countries, has concluded that each technical problem is solvable, though many will require decades of development. Breakthrough Starshot is, in its way, the most honest answer to the interstellar travel problem yet proposed. It accepts the speed of light as a wall. It refuses to waste time trying to break it. It simply asks how close to the wall human engineering can get, and how usefully we can design a mission around the best achievable speed. 1/5 of light speed. A journey measured in decades rather than lifetimes. A postcard from another star system, arriving on Earth within the lives of today's children. The project remains in early stages. The laser array has not been built. The sail material is still in laboratory development. Funding is uncertain, but the concept has survived every technical review it has faced. It is the benchmark against which other interstellar proposals are measured. In the 1950s, a team of physicists working at General Atomics in San Diego proposed a spacecraft that would travel to the stars by detonating nuclear bombs behind it. The concept was called Project Orion. It was led by the theoretical physicist Theodore Taylor and involved the mathematician Freeman Dyson, who would later help evaluate Breakthrough Starshot almost 60 years later. Orion's design was brutal in its simplicity. A massive steel plate called the pusher plate would be attached to the back of the spacecraft through a system of shock absorbers. Small nuclear bombs would be ejected from the ship and detonated a short distance behind the pusher plate. The blast would slam against the plate, pushing the ship forward. The shock absorbers would spread the impact over several seconds, preventing the crew from being crushed. Then another bomb, then another. The ship would ride a sequence of nuclear explosions toward its destination, each one pushing it faster. The cadence would be about 1 explosion per second. The numbers were extraordinary. Orion could reach Mars in weeks, Jupiter in months. A larger version, the so-called Super Orion, could achieve 10% of the speed of light using a sufficient supply of bombs. That speed would carry a crew to Alpha Centauri in about 40 years, a single generation. A mission completable within the career of a young astronaut. The concept was not a pipe dream. General Atomics conducted small-scale tests. They built a model spacecraft powered by conventional explosives, launched from a proving ground in the American Southwest, to verify that the pusher plate principle worked. The model, about 3 feet across, successfully flew to a height of several hundred feet using a series of small charges. The physics worked. The engineering worked. The political reality did not. Project Orion died in 1963, when the Partial Test Ban Treaty was signed. The treaty prohibited nuclear detonations in the atmosphere, underwater, and in outer space. Orion, whose very operation required thousands of nuclear explosions in orbit and beyond, became illegal by international law. Dyson, who had fought for the project, later wrote that he was relieved by its cancellation. He had come to see the radioactive fallout that Orion would produce during its Earth-based takeoff as unacceptable. Even a single launch would spread radioactive particles across the planet. The crew would survive. thousands of unsuspecting civilians downwind would not. The project left a quiet legacy. Orion proved that a spacecraft could, in principle, achieve a substantial fraction of the speed of light using only established nuclear physics. The concept did not require new science. It required only the willingness to build and use enormous numbers of nuclear weapons in space. Every variation of Orion since has tried to find a way to avoid that political and ethical catastrophe. Later designs, such as the Daedalus project developed by the British Interplanetary Society in the 1970s, used controlled inertial confinement fusion instead of fission bombs. Daedalus was studied as a theoretical flyby mission to Barnard's Star, a nearby star system. Its designers calculated that a two-stage fusion rocket could reach 12% of light speed and cross the interstellar gap in about 50 years. Daedalus was never built. It remains a paper study. Its successor concepts, including a project called Icarus developed in the 2010s, continue to refine the idea. Nuclear propulsion, fission or fusion, remains the most powerful rocket technology that current physics actually permits. A more extreme fuel, however, exists in theory and has been produced in trace amounts in laboratories. It is also the most expensive substance humans have ever created. 1 gram of antimatter, reacted with 1 gram of ordinary matter, releases energy roughly equivalent to the detonation of a 43 kiloton nuclear bomb. Triple the yield of the weapon dropped on Hiroshima, from 2 grams of fuel, less mass than a paperclip total. Antimatter is the single most energetic substance permitted by physics. Every particle of ordinary matter has a mirror-image antimatter counterpart. An electron has a positron. A proton has an antiproton. When matter and antimatter meet, they annihilate each other completely. Every atom of their combined mass converts directly into pure energy in the form of gamma rays and high-energy particles. There is no waste. There is no residue. All of the rest energy, the energy that Einstein's famous equation describes, is released. For rocket propulsion, this is the ultimate possibility. A ship powered by matter-antimatter annihilation could, in principle, reach speeds of about 70% of light speed. A crewed mission to Proxima Centauri would take roughly 6 years of ship time, accounting for time dilation effects. Such a ship would change the calculus of interstellar travel entirely. The problem is making the fuel. Antimatter does not exist naturally in usable quantities. Trace amounts appear in cosmic rays and certain radioactive decays, but the particles are scattered, fleeting, and impossible to collect in bulk. To obtain antimatter for a rocket, you have to manufacture it. The process is performed at only a few facilities on Earth. The largest is the CERN Particle Accelerator Complex on the French-Swiss border. CERN produces antiprotons by smashing ordinary protons into a metal target at enormous energies. A tiny fraction of the collisions produce antiprotons. Those antiprotons are then captured, cooled, and stored in magnetic traps that prevent them from touching ordinary matter. The quantities involved are almost incomprehensibly small. In the 2010s, CERN produced approximately 1 billionth of a gram of antiprotons per year. A full gram of antimatter, enough to fuel a single interstellar mission, would require billions of years of production at current rates. The cost is equally absurd. Economists have estimated that 1 gram of antimatter, given current production technology, would cost approximately 60 trillion United States dollars. More than the annual economic output of the entire planet. A single Starship tank of antimatter fuel would require multiple grams. A fleet of antimatter-powered ships would require a production infrastructure larger than any industrial project in human history. New production methods have been proposed. Some theorists suggest that antimatter could be produced in bulk using dedicated solar-powered particle accelerators, possibly located in orbit. Even in optimistic scenarios, such facilities would take centuries to build and decades to produce a usable amount of fuel. Storage is also brutal. Antimatter cannot be held in any ordinary container. Any contact with ordinary matter causes immediate annihilation. Current storage uses magnetic traps, called penning traps, that suspend the antiparticles in vacuum using electromagnetic fields. The largest traps can hold only about 1 trillion antiprotons at a time, which is still a microscopic fraction of a gram. A starship's fuel tank would need to hold grams or kilograms of antimatter stably for years. Despite these obstacles, antimatter research continues. Every year, scientists at CERN and other facilities refine storage techniques, study the properties of antihydrogen, and incrementally improve production rates. Antimatter propulsion remains, on paper, the most powerful rocket technology consistent with known physics. Whether it ever becomes a real Starship engine is a question for a civilization with vastly more energy and industrial capability than our own. If the speed of light cannot be broken, perhaps the solution lies in making the crew indifferent to the duration of the trip. Cryogenic sleep, once a staple of science fiction, has become a topic of serious aerospace research. The concept is straightforward. A crew member's body is cooled to a temperature just above freezing. Metabolic processes slow to near zero. The heart beats once every few minutes. The brain sustains minimal activity. Aging essentially stops. A 50-year journey feels to the sleeper like a single unbroken night. The idea sounds fantastical. It is, in modified form, already being done. Hospitals routinely use therapeutic hypothermia on patients who have suffered cardiac arrest or traumatic brain injury. The patient's body is cooled to about 91 degrees Fahrenheit for 24 to 48 hours. The cooling slows cellular damage and gives the brain time to recover. Thousands of patients each year survive because of this technique. Deeper cooling has been achieved in specialized surgical procedures. The technique is called deep hypothermic circulatory arrest. The patient's body is chilled to about 60 degrees Fahrenheit. The heart is stopped entirely. Surgeons have up to an hour to perform operations on the aorta or the brain itself. The patient is then slowly warmed, the heart restarted, and normal function resumes. The procedure is risky, but it works. Research on longer duration cooling has progressed more slowly. The space agency NASA has funded studies since the 2010s on torpor, a medically induced state similar to hibernation. The research, conducted in partnership with a company called SpaceWorks Engineering, has demonstrated that human volunteers can be held in a mild hypothermic state for up to 2 weeks without significant harm. 2 weeks is not 50 years. The biological problem is that long-term cold storage damages tissues in ways the body cannot easily repair. Ice crystals form in cells, rupturing them. Blood chemistry changes in dangerous ways. Protein structures degrade. Even with cryoprotectant chemicals added, the damage accumulates over time. Animals kept in artificial torpor for weeks show physiological stress that becomes fatal within months. True long-duration cryosleep, the kind that would let a crew sleep through a voyage to another star, remains beyond current medicine. Several research groups are exploring workarounds. One approach studies the biology of natural hibernators. Ground squirrels and certain bears enter a state called torpor, in which their body temperature drops to near freezing for months without obvious tissue damage. If the biochemical mechanisms that protect their cells could be transferred to humans, long-term cooling might become possible. Another approach is cryopreservation. This involves replacing the water in a patient's body with cryoprotectant chemicals that prevent ice formation, then cooling the body to temperatures far below freezing. Small organs, such as rabbit kidneys, have been successfully cryopreserved and thawed, retaining some function afterward. Whole-body cryopreservation of humans remains speculative and has never been successfully reversed. A third approach involves chemical suppression of metabolism without significant cooling. Researchers are studying compounds that can slow cellular activity by factors of 20 or more. The technique could potentially extend human lifespan during a long voyage without the risks of deep cooling. None of these techniques is ready for an interstellar mission. Each faces challenges that will likely take decades of research to overcome, but the research is active. The number of laboratories working on the problem has grown every decade. Cryosleep, once pure fiction, is slowly becoming plausible science. If it does become real, the speed of light loses its sting. A ship that takes a century to arrive does not matter if the crew sleeps through the crossing. If a crew cannot sleep through a century-long voyage, another option is to live through it. Not the same crew, the descendants of the original crew. Generation ships are the oldest interstellar travel concept in science fiction. They date back to at least 1929, when the British physicist John Desmond Burnell sketched out a proposal for a hollow spherical world that could carry thousands of people across space for generations. The idea has been refined countless times since. The basic concept has remained unchanged. Build a spacecraft large enough and self-sufficient enough to support a small human population for hundreds of years. Launch it toward a distant star. Accept that the people who step off the ship will be the descendants of the people who boarded it. The engineering challenges are staggering, The ship must carry everything needed to sustain human life for centuries. Food production systems that can recycle waste indefinitely. Atmospheric systems that maintain breathable air through hundreds of thousands of hours of continuous operation. Water filtration, radiation shielding, replacement parts for every critical component, stored in volumes no realistic cargo hold could accommodate. The biological challenges may be worse. The minimum viable human population for long-term genetic health is a subject of active research. Some studies suggest a few hundred individuals carefully selected for genetic diversity could sustain a healthy population for many generations. Others argue the minimum is closer to several thousand. A crew below that threshold faces a slow slide into inbreeding, genetic disease, and eventual collapse. Psychological challenges are harder to quantify. Humans did not evolve to live in sealed metal environments for their entire lives. A crew born and raised aboard a generation ship would never see a horizon, never feel unfiltered sunlight, never experience weather. Their entire universe would be the interior of the spacecraft and the ever-shifting stars outside the viewports. Several detailed studies, including simulations run at the University of Strasbourg in 2017, have concluded that sustaining a psychologically stable human population across 15 or 20 generations in a sealed environment is plausible but fragile. Any significant disruption, social, medical, or technical, could spiral into collapse within a single generation. The ethical dilemma is perhaps the deepest. The original crew chooses to board the ship. Their descendants do not. Children born aboard a generation ship are conscripted into a mission they never agreed to. Their lives are bounded by the walls of a vehicle chosen by their ancestors. Some philosophers have argued this is no different from ordinary parenthood, where children are born into circumstances they did not choose. Others have argued it is a uniquely severe form of constraint, imposing a confined existence on every descendant for the sake of a goal that may not even be achieved. The arrival itself is not guaranteed to be triumphant. The crew that steps off the ship will not be the crew that launched. They will be strangers to Earth culture, speakers of a drifted dialect, products of a society shaped by centuries inside a tube. They may feel more loyalty to each other than to the humans who sent them. They may choose to settle the new world or continue wandering. They may conclude that the mission itself was a generational crime. Despite all of this, generation ships remain the most technologically achievable, interstellar crewed mission currently conceivable. They require no warp drives, no wormholes, no antimatter fuel, no cryogenic sleep. They require only very large spacecraft, sustainable life support, and centuries of human endurance. A civilization patient enough to accept the sacrifice could reach the stars. But if such civilizations are common, the galaxy should already be full of them. It is not. The Italian physicist Enrico Fermi asked a simple question over lunch with colleagues in 1950. If interstellar travel is possible at all, even slowly, the galaxy should be crawling with alien civilizations by now. The galaxy is around 13 billion years old. Any civilization that developed generation ships or warp drives or even just nuclear-powered probes could have colonized the entire galaxy in a few tens of millions of years, less than 1% of the galaxy's lifespan. So where is everybody? The question became known as the Fermi paradox. It has hung over the search for extraterrestrial intelligence ever since. Every radio telescope, every optical survey, every planet-hunting mission has contributed to the puzzle. We have catalogued thousands of planets orbiting other stars. Some of them sit in habitable zones, regions where liquid water could exist. Many of them are probably rocky worlds of roughly Earth's size. The galaxy contains hundreds of billions of stars. Statistically, some fraction should host civilizations. Some fraction of those civilizations should, by now, have spread across their neighborhoods. The sky, when we listen, is silent. No radio signals that look artificial. No optical signatures of engineered megastructures. No probes passing through our solar system. No colonies established on nearby worlds. Nothing that cannot be explained by natural astrophysics. Several hypotheses try to explain the silence. The first is that we are alone. Intelligent life may be far rarer than the optimistic calculations suggest. Perhaps the steps from lifeless rock to technological civilization require such an improbable sequence of accidents that Earth is one of the very few planets in the galaxy where they have occurred. If this is true, the galaxy is quiet because there is nobody to make noise. The second is the filter hypothesis. Some event in the evolution of a civilization consistently prevents it from reaching the stars. Perhaps technological societies destroy themselves through nuclear war, environmental collapse, or runaway artificial intelligence before they can expand beyond their home planet. Perhaps the filter lies ahead of us, waiting. Perhaps it lies behind us, and we got lucky. The third is that interstellar travel, even at slow speeds, is harder than the simple arguments suggest. Generation ships may fail at rates high enough to prevent successful colonization. Cryosleep may never work well enough. The biological and social challenges of crossing space may defeat every civilization that tries. If this is true, the galaxy is silent because nobody has figured out how to cross it. The fourth is that someone is out there, but we cannot see them. Civilizations may deliberately hide from younger species. They may communicate through physics we have not yet discovered. They may be so alien that our detection methods simply do not register their presence. The fifth is more unsettling. Civilizations may be common, briefly. A civilization that learns to manipulate the speed of light may also learn to manipulate itself into extinction. The same physics that enables warp drives may enable weapons that end worlds. Every civilization that gets close to crossing the light barrier may destroy itself before completing the crossing. The Fermi paradox has no accepted solution. It is one of the hardest puzzles in all of science. Every proposed answer has problems. Every piece of data we collect narrows some possibilities while leaving others open. For a mission planner, the paradox is a warning. The galaxy either cannot be crossed, or it can be crossed, but the crossing changes the civilization that attempts it. Either answer should matter to anyone designing the first human interstellar mission, because the changes would be profound. A working warp drive would not be a quiet technological advance. It would be the single most disruptive event in human history. The first demonstration would likely be small, a laboratory bubble, perhaps the size of a grain of sand, producing a measurable space-time distortion, a video released by a research team, a paper in a major journal. Within hours, every scientific publication on Earth would carry the story. Within days, every stock market would react. The economic consequences would be immediate. Space-based industries, which had spent decades slowly building infrastructure based on chemical rockets, would face instant obsolescence. Satellite constellations designed to orbit at specific altitudes would become competitors with ships that could simply appear above any point on Earth. Communications infrastructure, which currently relies on the slow crawl of radio signals across the solar system, would be disrupted by vessels capable of carrying messages at effective speeds beyond any transmitter. The military consequences would be faster. Every defense planner on every continent would immediately recognize that a warp-capable spacecraft represents a weapons platform of unprecedented reach. A ship that can arrive from another star system in days or hours has no defensive perimeter. The concept of a secure border, which has governed international relations since ships could cross oceans, would require redefinition. The geopolitical consequences would reshape the map. Nations that had invested heavily in warp research would suddenly hold strategic advantages, equivalent to those of nuclear powers in the 1950s. Nations that had not would scramble to catch up, or to negotiate access, or to accept permanent second-tier status. The treaties and alliances of the current world would be renegotiated within a generation. The economic resource picture would shift. Asteroids, which are currently visited by only the most expensive uncrewed probes, contain more platinum, nickel, and rare Earth elements than all known terrestrial reserves combined. Warp-enabled mining ships could reach them in hours. The value of terrestrial mines and the economies built around them would collapse. Entire industries would relocate off-planet. The timeline of human expansion would compress. Currently, mission planners at space agencies talk about Mars colonies in timescales of decades. A working warp drive would turn Mars into a short trip. Colonies on moons of Jupiter and Saturn would become feasible within a few years of the drive's development. Missions to the nearest stars would follow within another decade. Culture would strain. Humans are adapted to a planet. A species scattered across dozens of star systems would fragment. Earth-based governments would struggle to maintain authority over distant colonies. New political structures would have to be invented. Some would probably fail. Even the concept of home would change. A working warp drive would mean that any human, in principle, could live anywhere in the reachable galaxy. The places where our ancestors lived, where our languages developed, where our histories played out, would become optional. Human identity, tied for all of history to a single planet, would need to find new anchors. Science itself would leap forward. The ability to visit other star systems directly would end the era of remote astronomy. We would stand on planets we currently see only as smudges of colour in telescope images. We would sample alien atmospheres, geology, and perhaps biology firsthand. The list of mysteries that could be investigated in a single human lifetime would grow by orders of magnitude. All of this hinges on a technology that currently exists only in equations, in simulations, and in tiny Casimir experiments that have not yet been verified. Whether any of it becomes real depends on whether the math on the page can survive contact with the laboratory. Which brings us to the question every mission planner eventually has to answer. Of all the options surveyed, which one actually delivers us to the stars? After every proposal, every equation, every laboratory test, a decision has to be made. What do we fly? The warp drive sits first on the list of dreams. Alcubierre's original design was mathematically elegant and energetically impossible. The updates from Harold White, Eric Lentz, Alexei Bobrik and Gianni Mater each trimmed the energy budget. The most recent work reduces the exotic matter requirement to 0, using only ordinary matter in precise geometric arrangements. The nanoscale warp bubble experiments, if they are real, would be the first direct laboratory evidence that space-time can be shaped by human machinery. The technology remains decades, probably centuries, from a working starship. It is not impossible. It is not close. The mission planner files it as a long-term research priority. The wormhole sits second. Traversable wormholes require exotic matter in quantities no laboratory has produced. The Morris Thorne blueprint describes them in detail. Nothing about the physics forbids them outright. But the engineering is further from reach than warp drives. A wormhole needs a stable, macroscopic tunnel through space-time, propped open by negative energy densities that dwarf anything the Casimir effect has demonstrated. Wormholes remain a theoretical possibility and a practical impossibility for the foreseeable future. Quantum tunneling and the search for tachyons the mission planner sets aside. Neither provides a usable method of crossing interstellar distances, regardless of the theoretical loopholes. Cosmic inflation and the expansion of the universe are informative but not actionable. They prove that space can move faster than light. They do not tell us how to make space move that way under our control. The M drive, after a quarter century of controversy, is dead. The Heim theory drive never had the foundation to begin with. What remains are the methods that respect the speed of light. Breakthrough Starshot is the nearest term option. Laser-push sails carrying chip-sized probes to Alpha Centauri at 20% of light speed. The engineering is hard but well understood. The first interstellar images could reach Earth within a single human lifetime, starting from a launch sometime in the next several decades. It is a probe mission, not a crewed mission, but it is a mission we could actually conduct. Nuclear pulse propulsion, in the style of Project Orion, offers the best crewed option consistent with known physics. A fusion-based variant could reach 10 to 12% of light speed, delivering a crew to Alpha Centauri within 40 to 50 years. The political and environmental obstacles remain severe. The physics is solid. Antimatter propulsion offers higher speeds, perhaps up to 70% of light. The fuel costs are astronomical. The storage problems are unsolved. If a civilization develops fusion-scale energy production in orbit, antimatter becomes viable on a timescale of a few centuries. Cryogenic sleep and generation ships are supporting technologies rather than propulsion methods. They make slower ships tolerable for crews. Generation ships require no new physics. They require unimaginable commitment from multiple generations of humans. The verdict of the mission planner, in the early 21st century, reads something like this. The speed of light is still the wall. Every method that claimed to break it has either failed experimentally or remains mathematically consistent while being engineeringly impossible. Every method that respects it offers a slow, difficult, decades-long crossing. The first real interstellar mission, when it launches, will almost certainly be a probe pushed by light. The first crewed interstellar mission, if it ever launches, will probably ride nuclear fire across a gap that takes decades to cross. Generations will be born and die before the voyage ends, and yet the research continues. The laboratory warp bubble experiments continue. The Casimir cavity measurements continue. The papers proposing new warp geometries continue to appear in respectable journals, because the math keeps saying no, and the humans keep trying anyway. The star that sits 4 light-years away is waiting. Whoever finally reaches it will do so having either cracked the code written into the fabric of the universe, or having spent a lifetime sealed inside a metal shell, travelling the hardest, coldest, most honest road physics allows. Either way, the journey starts with a decision we have not yet made, and a ship we have not yet built,